Mick Sagrillo has been installing, repairing, and remanufacturing wind turbines at his wind-powered shop near Forestville, Wisconsin for the past 16 years. To date, he has repaired or installed over 1,000 wind-powered electric generators.
The power available in the wind, if we define power as P, power available in the wind is equal to 1/2 of the density of the air, and that makes sense because we're dealing with a fluid, and the denser a fluid is, obviously the more impact that the molecules in that fluid are going to have. So we add density of the air times the swept area of the rotor, and the swept area of the rotor is the circle that's defined by the blades. The larger the swept area, obviously, in other words, the bigger the blades, obviously the more collector we've got, and the more power we're going to be able to extract out of the wind. And the third factor in the equation is wind speed, the velocity of the wind, cubed. This is an extremely important part of the equation, V cubed. What it tells us is that if we want to create power, we can either do it by making the air more dense, which isn't an easy task. We'd have to wait until winter, for example, in order for that to happen. Or we can put bigger blades on the wind generator. That's going to cost us a bit. Or we can do it by increasing wind speed. And the nice thing about increasing wind speed is, because the fact that wind speed is cubed, every time we do one thing to the wind speed, essentially it comes back to us 3 times, because V cubed essentially means velocity times velocity times velocity. Now, the way we can do that is by increasing the height of the wind generator above the ground level. What we're trying to do is, we're dealing with a fluid, and just like a stream that's flowing along a bank, the further you get out away from the bank, the faster the stream is flowing, the swifter the stream is, because there's less friction between the stream, the water, and the bank. So the further we get away from the surface of the earth, the less influence we have of ground drag on the velocity of the air, and the air moves a whole lot faster. So one of the key things that we need to do is, or remember, is always increase tower height whenever we possibly can. The best way of doing it is to contact your local Weather Bureau or airport and get an average wind speed from one of those 2 sources. Now, I have to start out by telling you that the data that you get is going to be rather poor, and the primary reason is because an airport or a weather bureau might be measuring at a distance of 18 to 20 feet, 22 feet maybe above ground, and a wind generator is going to be way up here at 80 or 100 feet above ground. The reason they do that is because they're monitoring wind speed where people live. Because that's what people want to know. That's fine, except for the fact that, remember, we were talking about ground drag, and we were talking about the further you get away from the surface of the earth, the stronger the winds are. So what we need to do is figure out some way of coming up with, if we know that the wind speed down here is such and such, is that enough of a wind speed to justify a wind generator up at this height? And it turns out that the average wind speed you need to make a viable installation, wind installation, is relatively low. 7 miles an hour would make a fine wind installation. If we monitored at 18 feet for Weather Bureau data, or 30 feet, a 7 mile an hour average wind speed, that would extrapolate up to about 9.5 or 10 miles an hour at 100 or 120 feet. That's a great resource, wind resource, for a battery charging installation. If it were a grid intertie installation, we might want to start at maybe 9 miles an hour at ground level. First of all, the wind generator can only produce so much power. If you go beyond that amount, for example, if you spin the generator so fast that it wants to produce 1,500 watts and it's only a 1,000-watt wind generator, well, you're going to burn up the wind generator. It'll do it for a short period of time. It'll produce that amount of power, but eventually it's going to destroy itself just from heat buildup. The other thing is that as as everything, for example, the blades are spinning faster and faster and faster, centrifugal forces are pulling on the blades and all the various different components, and they're going to try to tear it apart. So what we need to do is we need to spoil that wind somehow and get rid of some of that, reduce some of the centrifugal forces. And again, one way of doing it would be pitching the blades up out of the wind, the other would be pitching the blades sideways out of the wind. We'll take a look at a couple of wind generators that do that. If you take a look at the machine from the underside, if we look at it from down here, you notice that we've got the wind generator sitting on the tower, but the wind generator isn't directly over the tower. It's actually offset from the tower to one side. And also, this pin is not vertical, which means the tail does not sit vertically. It actually is canted off to the side slightly. Well, if the wind generator is not directly over the tower, that means that the rotor, this spinning disc, isn't directly in line with the tower as well. It's actually offset to one side. So as wind speed increases and the pressure on the blades increases, this spinning disc is going to have a tendency, since it's not lined up with the tower, it's going to have a tendency to try to walk around the tower. And that's exactly what it does, is it moves around the tower. And if the wind is coming from that direction and it's blowing against this rotor, as the rotor moves around the tower, there's less exposed area to the wind. And if there's less exposed area, then there's less power coming to the wind generator, and the wind generator can spoil or spill off some of that excess, some of that power by basically having a smaller face into the wind. Okay. The purpose of the tail being offset is, let's assume that we've got the tower, the wind generator, out of the wind because the wind pressure is blowing on it. What could possibly make this rotor face back into the wind? If wind is blowing against it, there's really nothing to bring it back into the wind. By cocking the tail slightly, what we do is we bring gravity into the whole situation, and we use gravity to bring the tail, to realign the tail back into the wind, and therefore the rotor back into the wind. Notice what happens to the tail. Look at the bottom edge of the tail, and notice what happens to the tail as the wind generator cocks around. The tail moves up. If the tail moves uphill and the wind stops, gravity is pulling on this tail, is going to realign the wind generator into the wind and pull the machine back down. Gravity pulling on the tail actually realigns the machine back into the wind. This machine governs slightly differently. It's essentially the same idea, that is, pitching the blades out of the wind some way, but rather than side facing, the wind seeker uses a slightly different technique in that it pitches the blade up and over the top of the tower. So what happens is, as wind pressure increases on the rotor, it begins pushing the rotor, and since the rotor is spinning above a pivot point down below, this allows the wind generator, as wind pressure increases, it allows the wind generator to want to cock back with increasing pressure, to cock back and out of the wind. And as it does that, as it cocks back out of the wind, again what you see is you see a smaller disc that is facing the wind. And if we've got a smaller disc, a smaller swept area, we're going to be producing less power. Another thing about the power equation is this power equation assumes a fixed pitch on the blades. It's assuming that the blades are in the ideal plane, the ideal location for generating power. What were to happen if we were to take these blades and we were to pitch them some way and cause them to be less efficient? Well, there's a governor that exists that does that as well. And that's a blade-activated governor. The blades are on a shoe on the top and bottom of this governor, but they're free to move on a shaft. But they're not free to move independently. They're actually coordinated with a spider or a synchronizer behind it. But again, we're dealing with a spinning mass, and we're dealing with centrifugal forces. And centrifugal forces are going to pull on the blades against the tension of the springs. And as they pull on the blades, an interesting thing happens if you watch the governor and the synchronizer. As they pull on the blades, what happens is they move away from the hub. The blade shoes move away from the hub of the wind generator, but the synchronizer causes them to pitch. What happens if we were to pitch these blades? Well, if we start pitching these blades either into or out of the wind, then what's going to happen is they're going to be less efficient at extracting power out of the moving air, out of the moving wind. And by doing that, by using centrifugal forces to pitch the blades out of the wind, we can actually reduce the efficiency of the blades, and the rotor will spin slower. An interesting thing happens with a two-blade machine versus a three-blade machine. The more blades that a wind generator has, the more each blade sort of spoils the air for the blade behind it. So in building a wind generator, the fewer the number of the blades you have, the better off you are, because the more efficient the rotor is at converting wind into electricity. An interesting thing happens with a two-blade machine as it yaws, depending upon whether the blades are vertical or whether they're horizontal. At one point, when the blades are vertical and in line with the tower, it's very easy for the machine to yaw. But as soon as the blades turn, you know, in a fraction of a second, a quarter turn, and are in a horizontal position, then this rotor exerts maximum resistance to wanting to yaw or want to turn out of the wind as the wind is shifting. We've got a stopping motion, blades turn, it's free to yaw, blades turn again and it stops, blades turn again a quarter of a turn and it's free to yaw, blades turn again a quarter of a turn and it stops. And what appears to happen is a chattering with the wind generator blade, and that chattering or that vibration is eventually going to fatigue fasteners, maybe welds. All the various different components of the wind generator are going to be stressed over time due to that chattering. With a three-blade rotor, again, you don't have that situation. It yaws very freely, and as a result, a three-blade rotor is much, much easier on all of the various different components, the welds, the fasteners, and everything else. Let's just sort of take a look at what we've got here. I've got a shop, a block shop building that happens to be, it's 21 feet tall without the chimneys. The barn to the west of it is 28 feet tall, and behind it I've got a silo that's about 45 feet tall. The basic rule of thumb is we want to be at least 30 feet above anything within 500 feet. In the summertime, the prevailing winds come out of the south and out of the southwest, and in the wintertime my prevailing winds come out of the north and out of the northwest. In the summertime we also get storms that come out of the west, directly out of the west. So if we take a look at the silo in relationship to the wind generators, that's the tallest object, ideally we'd like to be upwind of any objects that are going to cause turbulence, namely the silo or the barn. This machine is, it's definitely upwind of for our prevailing winds in the summertime, but it's downwind in the wintertime. So again, my basic rule is I want to be at least 30 feet above it. This tower I've sited at 80 foot. The silo is 45 feet. So I'm 35 foot above that obstacle. This is a good sighting. The ideal place would actually be to the west of the barn. If I was anywhere, if I had a tower anywhere to the west of the barn, then I could take full advantage without any obstructions at all, no turbulence, to the northerly winds, the northwesterly winds, the southwesterly winds, and the southerly winds, and also the winds that come out of the storm-related winds that come directly out of the west. So without question, that's the best place for a tower on this particular piece of property. Okay, we're going to try to determine how tall this tree is here, relatively short tree, and we're going to do it with a shadow method. This isn't the best time of day to do it. It would be better to do it at the middle of the day because then the shadows are a little shorter, but it'll still work. What I'm going to do is stick a shovel upright and into the ground and measure the height. I'm at 4 foot 2 inches. Let's make this easy by going down 2 more inches. Okay, now I'm at, buried the shovel completely, but I'm at 4 feet. And let's see, Okay, I see where the... I'm going to measure the length of where I'm at. Okay. I'm at about 26 feet is the length of the shadow, and the length of the shovel is 4 feet. Remember those numbers. Now, let's figure out how long the tree shadow is. And I'm going to take my tape measure and hook it into the ground, and I'll keep it in place with my pocket knife. Let's go for a walk way out to the end of the tree shadow. All right, let's run the tape measure out as far as it'll go, and hopefully our tape measure is going to be longer than the shadow of the tree is, and it's not. I'm at 100 feet here, and my my tree shadow winds up a little bit further down here. Okay, so I'm going to go to about this weed is where it looks like the tree shadow ends, right about here. So if I'm at 100 feet here and I know how long my pace is, I can pace this off. I've got 2 paces, which for me is about 5 feet. So I'm looking at a tree shadow of 105 feet. Now, what we need to remember is the shovel was 4 feet tall, the shovel shadow was 26 feet long, and the tree shadow is 105 feet long. Now we can go in and figure out with a piece of paper and a pencil exactly how high our tree is. All right, remember I said that the shovel was 4 feet tall, and that its shadow, the shovel shadow, was 26 feet tall. So we know if we divide 4 into 26, that for every foot of shovel, we've got 6 1/2 feet of shadow, okay? Now, if the tree shadow was 105 feet tall, and we divide 105 by 6 1/2, what we wind up with is the tree height, and we've got 105, and we divide that by 6.5 in our calculator, and it comes and tells us that the tree height is just over 16 feet tall. And what we can do is we can use a similar technique for finding the height of any obstacle that we need to sight around, if that's another tower, or if it's the silo, or if it's the barn, or the shop right here, or the house. Any obstacle at all, we can use a similar type of ratio to determine what those heights are, and make sure that we sight our wind generator, or we size our tower to be at least 30 feet above that height, that obstacle height. And again, that's a minimum. The higher we go above that, the more power we're going to get from the wind generator, because again, the higher you go, the more fuel there is, the windier it is. The 3 different types of towers would be a freestanding tower, a guide tower, and then a tilt-up tower. A freestanding tower would be similar to an old water pumper tower that we're all familiar with. It has a very narrow footprint. That means it takes up very little space on the ground. Towers, when you buy a tower, you're essentially buying steel, and it takes a whole lot more steel to build a freestanding tower and keep it standing upright than it does, for example, a guide tower. So freestanding towers would be the most expensive. We'll get to cost in just a second. Then we've got guide towers, which are somewhat flimsy. It's like maybe putting up a 100-foot extension ladder. But once you guy it off in 3 different directions, and the soil holds it in place, they become extremely rigid, very, very solid. They don't go anywhere. Those are the lightest towers, and therefore they're the cheapest towers. And then a third type of tower would be a tilt-up tower, which is a variation of a guide tower. It's guide, but it's guide in 4 directions. And again, this is the tower that we can tilt up and down, so that we can work on a tower, you know, from the comfort of the ground. Well, some people don't like guy cables, or they may have a situation where the guy cables would be intrusive in their yard. They don't like what they look like aesthetically, so they would choose, for example, a freestanding tower at a slightly higher cost. Also, they take up less space, a smaller footprint. That would be another reason why you might want a freestanding tower. Two things that need to be considered with a freestanding tower and a guide tower is the fact that you have to climb them. And if you're deathly afraid of heights, there's nothing wrong with a good fear of heights, but if you're deathly afraid of heights, then you may want to consider a tilt-up tower, because you can have a wind generator 100 or 120 foot tall and still work on it from the comfort of the ground, maybe sitting on your lawn chair sipping a mint julep on a Saturday afternoon. You can have a wind generator and never have to climb the tower in order to do any maintenance or any repairs on it. As far as cost goes, let's start with the cheapest of the three, that being the guide towers. Those towers, depending if you're buying a new tower or a used tower, may cost you anywhere from $20 to $30 a foot. So a 100-foot tower would run you $2,000 to $3,000, for example. That's for the hardware, the cables, the anchors, the tower itself, all the fasteners, the tower top. It would be the complete tower, but wouldn't include the concrete or the rebar that goes in the concrete, or any of the installation at all. On the other hand would be freestanding towers. And freestanding towers cost the most because we're paying for the most amount of metal. Those towers would probably run you anywhere from $40 to $50 a foot for the complete tower. And in between there would be tilt-up towers that would cost somewhere between maybe $30 and $40 a foot. The easiest to install yourself is, without a doubt, is a tilt-up tower. You need more room for the guide cables, and you need to have a runway in front of the tower so that you can pull the tower up. But without a doubt, that's the easiest tower. The towers are configured in such a way that you have couplings that connect the various different pipe sections together. You run the cables out and connect them to your anchors once the anchors are in place. And then you tilt this whole thing up, adjust the cables, and you're in business. You know, you've got a tower that you can now install your wind generator on. On the other extreme would be a freestanding tower or a guide tower that you would install with a gin pole, piece by piece. In other words, what you would do with it would be start out with maybe the bottom 20 foot of the tower that you'd get upright, and then you would install sort of a davit or a gin pole, a miniature type of crane that would bolt onto the tower itself. And using cables and rigging, you'd pull the pieces up individually and assemble the tower. As you were going up in height, you'd continue to increase this gin pole up higher and higher and higher, and bolt the pieces together. Very time consuming, usually involves a crew of several people at a minimum. You'd need to use that type of situation where you might be on an island in the middle of the ocean, for example, or you're in the middle of a forest where you can't get a crane in, you can't tilt the tower up and down. And then in between those two, another situation would be where you were to assemble the entire tower on the ground, for example, be it a freestanding tower or a guide tower, bring a crane in and have the crane lift the tower up and then bolt it down in place. If it's a freestanding tower, bolt it to your anchors, or if it's a guide tower, lift it up, pull the guide cables out, and attach it to your anchors that have already been poured in the ground. If this is our ground level, what we'd want to do, and let's say that this is our anchor going down into the ground, we'd want to encase it in concrete, and the concrete would be in the shape of an inverted trapezoid, for example. This could actually go up to the surface of the ground. It doesn't much matter. But by using this inverted trapezoid, if we were to try to pull it out, rather than coming straight out, it would take with it a whole cone of soil. So by using an inverted trapezoid shape, we actually utilize more soil around the concrete footing to hold it in place. The one thing that you need to be careful of in putting concrete in the ground with an anchor is that you need to know where your frost line is. That means what is the depth to which the ground freezes in the wintertime, if that's a problem where you live. In my region of the world here in northern Wisconsin, we have an average frost depth of 4 to 5 feet. That means that I want my anchors to be, if this is my frost line, I want my anchors to be at least 6 inches below that 4 to 5 foot frost depth, let's say 5 foot. So I would make my anchors 5 foot 6 inches deep at the bottom. And this is so that frost can't get underneath the anchor and heave it out of the ground. If that were to happen, your whole wind generator tower would fall over. Well, remember, most of these renewable energy systems are 12, 24, maybe 48 volts DC going into a battery bank. That's fine, but remember, as my voltage is down, my current has to be up there. And the current that you can run is a function of the wire that you have, the size of the wire. If I run low voltage at very high current, I've got to have extremely heavy wire to run any distance. In order to get around the current problem, the low voltage, high current problem with DC systems, what wind generator manufacturers have done is gone to 3-phase AC wind generators. And in a 3-phase AC wind generator, you actually have 3 coils of wire in the wind generator, each producing current. Those 3 phases actually are responsible for 1/3 of the total current, whereas in a DC system, 1 wire carries all of the current. In a 3-phase AC system, each wire is responsible for 1/3 of the current. As such, I can get by with much, much finer wire, much smaller gauge wire than I could if this were just a straight DC system. If this were just a straight DC system and I'm running the distance from here to the battery bank in the shop, I'd probably be dealing with wire rather than this gauge, which is about the size of, slightly larger than, maybe twice the size of a pencil lead. I'd probably be dealing with wire the size of the wire itself, the size of my little finger, almost the size of welding cable. That is extremely expensive wire compared to a finer gauge wire like this. Now, the question is what do I do with 3-phase AC? I can't put that in my battery bank. Not true. What we do with this current, once it's in the shop, or once it's in wherever you're going to be storing it in a battery bank, is we would run it through a bank of diodes, and the diodes would convert the 3-phase AC to DC, and the DC would then go right into my battery bank. Very simple. What we're going to do is take the ends and strip the very end of the wire, the plastic insulation off the very end of the tower wires, and make sure that those go in your pocket. There's enough garbage out there. Okay. And now it's time to take a couple of, these are called split bolts, basically a bolt with a nut on it that has a split that the wires can go into. And put one of the generator wires in there, one of the tower wires in on the other end. Take it down by hand a little bit. Grab the end of the split bolt with your tool of choice. My tool of choice in this case is a small vice grip. And then use a ratchet to tighten down the other end of the split bolt, the nut on the split bolt. And now we need to insulate this from the other wires and from the tower. So we're going to do that with a very healthy dose of electrical tape.
Does it matter which one you attach to which?
Nope. There is, remember, it's 3-phase wild AC. And In this case, the three-phase wires are hot to each other. They're not hot to ground, they're not hot to anything except to each other. And we're going to take this when we're done with it and rectify the output to DC anyway. So it really doesn't matter at all which wire goes to which. We don't have to observe polarity because there basically is none. The wind generator is now hooked up, wired to the controller in the battery room. And we're now ready to bolt the wind generator itself to the stub tower. You'll notice that what I've got attached to the tower wiring, to the ground of the ground wire of the tower wiring, is what's called a thimble, and it's being held on by a small cable clamp. And what the thimble is holding is an eye bolt. And what we're going to do with this eye bolt is we're going to pass it through a hole in the tower, and the eye bolt is going to hold the wire up, okay? Because this wire is very heavy. The length of the wire in the tower, it may weigh, oh, I don't know, it might weigh 70 or 80 pounds. And all that weight is pulling on the tower wire, the wires for the wind generator. And if we put that kind of weight on the wires coming out of the wind generator, we'd pull the wires right out of the bottom of the wind generator, and then we'd be in for some serious repair. So in order to avoid that, I'm going to pass the end of the eye bolt through a pre-drilled hole in the tower and take a nut. And one thing that we do with wind generators quite often is use a special type of a nut known as a nylock, or a nylon locking nut, a regular nut, but at the end of it it's crowned and it's got a nylon insert in it. If you take a look at the bolts, the nuts that hold the blades on, you'll see the same thing. It's a standard nut, and then it's got this little crown on top, and you can see another color in there between the silver of the nut and the silver of the bolt. In this case, that other color looks like a blackish purple color. This is sort of a cream color. That's nylon, and what happens is it wraps itself around the threads so that the nuts on the wind generator bolts don't vibrate loose and fall off the tower. Time to put the wind generator, align the coupling where it's supposed to go, push the rest of the wire into the tower as best we can from this angle, and mount the wind generator on the tower. And the coupling of the machine slips right on. And I've got to get the holes in the coupling aligned with the tower holes. And run a bolt through. Its washer and nylock is on. And we're ready to put the tail back on that we removed earlier. And the machine is ready to be raised then. The pin that's used is stainless steel. We're using dissimilar metals and metals that don't corrode easily. To make for a more maintenance-free wind generator. The last thing you want to use on a wind generator when it's 80 foot in the air is things like, mild steel, for example, that's unpainted. It rusts and it's going to cause a maintenance problem somewhere on down down the road. And if we're going to put this up, and hopefully it's going to be up for the next 10, 20, or 30 years, we want to make sure that we use materials that aren't going to give us any problems down the line. Okay, the wind generator is assembled, and it's now ready to, we're now ready to raise the machine. What we're going to do is we're going to tilt this tower up. This tower is shaped something like the letter L, or yeah, like the letter L. And this pole that's right over here is the gin pole, the short part of the L. And the tower is actually laying down the long part of the L. And what we've got is we've got a pulley system attached to a tractor. And from the back of the tractor it comes to a pulley, goes up to a second pulley. You can see where the 4 cables attached to the tower, and the pulley system up there, and how they come down and they connect to the tower at various different locations. You can also see barely in the grass, the weeds are rather tall here, but you can also see cables that go out to the side, to the right side and also to the left side. These are the side guy cables that are used to hold the tower upright. Basically what we've got is we've got a tower and going between 2 triangles. The triangles are essentially the side cables, and they keep the tower in tension. You need a total of 4 anchors in order to tilt up a tower like this. You can't do it with less than 4. Let's go back a little bit. Here is the rear anchor. You can sort of see it underneath here. It's hidden by the tower, but there are 4 sets of cables attached to that anchor. Okay, there's that rear anchor. And if we go up a little bit further, I'll show you what I'm talking about with front anchors, or excuse me, front cables and side cables and rear cables. Again, remember, this is a 4-cable system, or a 4-guy system. We've got 2 side guy wires. We've got a guy wire on the one side that goes off to the left, a guy wire on this side that goes off to the right, and then we've got a guy wire that goes up to the gin pole. This is the front guy, and this is essentially what we're pulling with and pulling against. But if you take a look at underneath here, there is another guy cable, and this is the one that's attached to the anchor that's hidden behind the tower. So this is, again, it's a 4-guy system. It's guyed in 4 different directions. We've got a 3-guy system, and watch what happens. Let me put my foot at the base so it doesn't kick out, but watch what happens when we lower the tower. Let it down. Okay. Let it down. Go ahead and let it out. It would get to a certain point where down is to the side. And if that were to happen with a 100 or an 80-foot tower or a 120-foot tower, that kind of jerking motion, you'd lose the tower. It would be an extremely dangerous situation. All right, let's take this now, and let's keep it where it's at, Steve. Let's take it now and let's add a 4th guy cable to it. Let's, rather than having all of the guys 120 degrees apart, with a 4th guy we can now make them 90 degrees apart. So let's put one side cable over here, and our rear cable goes back here, and the other side cable goes 90 degrees around over here, and front cable stays where it's at. Okay. Now let's take a look at what happens when Steve lowers the tower. The side guys keep it exactly in place so that, hold it right there, keep it exactly in place so that it won't fall to one side or the other. What happens is the rear cable, as the tower comes down, the rear cable just slackens, and the side cables keep it from moving from side to side. The front cable is the cable we're lifting with, and if we lift the tower back up again, you can see what the purpose of the rear cable is. As the tower comes up into place, the rear guide cable keeps the whole tower from going over. Most radio and television towers that you see are 3 guide systems. That's the minimum number of guy wires that you can get away with and keep the tower erect. If you went to 2 guide cables, obviously the tower would fall to one side or the other. But most guide towers that are permanently guide are 3 guide systems. If you want your guide tower to be a tilt-up tower where the whole thing tilts up and down, then for safety reasons, you need to go to a 4-guide system. You can't safely raise and lower a 3-guide tower. This is Steve. He's going to be on the tractor for us, and he's going to be on a rather noisy tractor going in that direction. I'm going to be at various different places. At the beginning of the lift, I'm going to be all the way over by the wind generator to make sure that it doesn't bob up and down or anything. And I'm going to be a considerable distance from him. And we have to be able to communicate somehow. So what you do is you develop a certain set of hand signals. The signals that we usually use is if I point in one direction or shake my finger, that means to go in one direction or to move back in the other direction. Usually something like this means shut the tractor off. A fist either out or up typically means to stop where you're at. Don't shut the tractor off, but stop motion. So we've got move forward, move backwards, stop motion, and kill the tractor because we need to talk about something or other. Go ahead, Steve. You can't hear me anyway, but that's why we use hand signals. You want to be careful to stand clear of it because if for any reason something should go or something should give, you certainly don't want to be underneath one of the cables or underneath the tower. It's going up real nice, real slow, real easy. It's going up just like it's supposed to. You can see the rear cables are just starting to, they're all coming up off the ground. Now at a certain point, gravity on the gin pole is going to take over, and the tower is just going to sort of ease down on its own without without the loader actually pulling on it at all. It's about at that point right now. It's pivoted, it's balanced on its own at this point. And we've got the cable that attaches the front anchor to the gin pole, and it's all pre-cut. We know the length of it and everything, and it attaches to the gin pole with a screw pin shackle. And Steve's going to have to put a little bit of tension on the tower so that a little bit of tension on the tower. Stop right there so I can get the screw pin shackle in place, screwed in place. Okay, back up now. Come on back a little bit. Take the tension off the pulleys. Take the tension off the pulley. Tension comes off the pulley. Okay, stop, Steve. There's a pair of ropes that go to the gin pole on either side of the gin pole. They go down to the anchors. There's a definite purpose to this, and you need to never lower a tower with a gin pole without these side ropes. Remember we were talking about we're going to use a gin pole to raise a tower, and we're using a 4-guy system in order to safely raise and lower this thing. Well, the gin pole is actually a miniature tower, and we need the same 4 guys in 4 different directions in order to safely raise and lower the gin pole. These cables would be analogous to the rear guys. The pulley system is the front guy system, but in order to keep the gin pole from falling from side to side as we're raising it, we have to add a set of temporary guys to keep the gin pole from moving from one side to the other, because it will want to do that, and if the gin pole collapses, well, then you've lost the tower. That can be a very, very dangerous situation. So what we've added is just a set of temporary ropes. This happens to be generically called boat rope. It's not very strong, but it doesn't need to be in this particular situation. Once the machine was up and running and we had the pulleys disconnected, we could also take the ropes, these side ropes off that hold the gin pole. We could take them off and store them someplace because they don't need to be out. And actually this material would deteriorate in sunlight. You don't want to leave it out anyway. Okay, now that the tower's up, you can see how the pulleys are rigged. You can see the pulley at the front anchor, and you can see the other pulley up at the gin pole. And these pulleys are not permanent fixtures. These pulleys are removable. This pulley comes off with a pin and a hairpin, and then the upper pulley, here's the hairpin for the pin on this pulley, and this pulley comes out. And these get put away because we don't want these to rust up any more than they already are. And there's no need for them. They're only used when we raise and lower the tower. It's not a permanent part of the tower at all. So there's our tower. We're ready to lower this tower. And again, essentially, it's a reverse of raising. What I'm going to have Steve do is start the tractor up and pull. Go ahead. Okay, go ahead forward a little bit. Go ahead, Steve. A little forward. Oh, a little forward. A little forward. Okay, hold it there. Hold it there. I'm talking to myself, but he can see me signaling to him. I pulled the screw pin shackle out. That was holding the tower down. Lay this off to the side. Now what's holding the tower is the cable and pulley system. Steve, I'm going to signal him to come forward and release the tension on, back the tractor up and release some of the tension on the pulleys, on the cable. And come on back about 2 feet. All right, take some tension out of the cables. And what I'm going to do is walk up to the rear guy anchors, the rear cable, in order to overcome the weight of gravity on the gin pole, which is holding this whole tower in place. We've got some slack in the lifting cable attached to the tractor, and I'm going to pull on the rear cable, and I'm going to pull sideways so Steve can watch me. Come on back. Come on back. I'm going to pull sideways, and what I'm doing is I'm overcoming the force of gravity on the gin pole, and at some point I no longer have tension on the cable at all. I've let go of it, and the tower is now going back down on its own, and Steve is controlling it by paying out the cable on the gin pole. Well, the wind's picked up, and the Bergey's running, so it's probably time now to go on into the shop and hook it up to a battery bank, because right now it's still freewheeling. It's really not connected up to a load. And we need to hook it up to a battery bank and see what kind of power it's producing. I can use this mirror here to see if my machine's running, because from my vantage point inside the shop, I can't quite see the top of the tower and the wind generator. So I use that in order to find out if indeed we've got power coming in. And wires come in through the building and up through a brake switch and into, I guess you'd call it a whole series of controls here. There's actually lots of things that are doing, or lots of electronics that are doing various different things at various different times. But what we're interested in is just in this area right here. The wires come into a brake switch, and I can use this to turn the wind generator on and off from inside the building by what's known as dynamic braking. The three phases come in on these three lines, and I've got this fused in another area, and I really don't want fuses here. But what I'm interested in is, as far as a brake goes, is a copper wire that runs across the three leads, so that if I were to take the three leads and short them out, you'll see them spark. Okay, you'll see them spark, and what I'm doing is I'm shorting out the three phases of the wind generator, and that will bring the wind generator to a standstill up on top of the tower. And if you take a look at the wind generator, I can put the brake on now, and it will stop the machine. hoping it stopped?
Stopped.
Okay. If I release the brake, that allows power to come in, and the power comes in from this switch, the brake switch, and goes through a three-phase circuit breaker, and from the circuit breaker it goes up into the Berge controller. This is still three-phase AC. Okay. In the Berge controller, the three-phase AC is changed to DC power and is sent on to a set of meters. Here's my battery voltage and generating voltage, and here's the current that I'm running through this box, through the fuses, and then down into the battery bank that's below the workbench here. This happens to be a 24-volt system, so we've got a center tap here, but because of the fact that we deal with all sorts of different equipment, I can actually test equipment from 12 volts all the way up to 48 volts with this battery bank. Right now it's configured for a 24-volt system, and if we go back to the metering and we take a look at the ammeter in relationship to an odometer, and we can see that it's quite windy out there right now. It's averaging around 15 miles an hour, 16 miles an hour, and periodically it'll gust up to 25. But as battery voltage climbs up around 30, 31 volts, we'll watch the ammeter click off to 0. So what's happened is the controller has disconnected the battery bank from the wind generator. Now it's connected again. What it's doing is it's cycling back and forth based on voltage. As voltage goes up, it disconnects it. As voltage goes back down, battery voltage again goes back down, it reconnects it. And because my wind speed is so high, I'm really pegging this needle back and forth. Yeah, like most machines that are on the market today, this wind generator, because of the heavy use of stainless steel, has a very, very minimal maintenance. Over a period of time, you're eventually going to have to replace bearings, but you'd have to do that with any moving piece of equipment anyway. Stainless steel fasteners need to be checked periodically. My recommendation is twice a year. You should either tilt the tower down if it's a tilted tower, or climb your tower if it's a climbable tower, and take a look at fasteners and make sure that nothing has rattled loose or fallen out. Most all catastrophic failures that we've seen with wind generators, or even major maintenance problems, have been due to the fact that fasteners have loosened up someplace or other. And that's true with any piece of equipment that has moving parts, because whenever you have any kind of vibration like that, it may cause fasteners to loosen up. And again, remember, we're talking about the use of locking nuts on this equipment to mitigate that, to reduce that problem. But it still does happen, and it's still a very good idea to occasionally run up the tower and do some checking on your wind generator to make sure nothing has indeed loosened up. The only other maintenance item on a wind generator like this may have to do with the blades and the leading edge, where if the leading edge starts wearing badly, it should probably need to be replaced. Hopefully you would catch that before it wore to the point where it was wearing into the blade, and then you might have a little bit more of a wear problem to take care of. But the maintenance on this equipment, as it is with most pieces of equipment available today, is quite reduced compared to what they were even 10 years ago. What every tower person needs is some sort of a work belt or a safety belt that allows him to free his hands up. This is my belt, and there are lots of different examples or lots of different belts like this that are available commercially. They're rather inexpensive. However, it's important, regardless of what they cost, it's important to make sure, if you're going to be doing any tower work at all, that you have one of these, because what's your life worth? Right? Besides a belt, you need some sort of a lanyard system so you don't slip from the tower. And I've actually got two different lengths depending upon what I'm working on. If I want to be working close to the tower, I've got a narrow belt, and if I need to be reaching up and around, I've got a longer belt, and I leave these both on at any given time. This allows me to to lean out considerably out, a little bit more comfortable with this type of a stub tower in order to do this kind of work. In addition to a belt, a safety belt, the other thing that you need is just a tool pouch. This tool pouch is nothing fancy. It's actually a roofer's belt. People that do roofing installations would use this as a nail pouch, and I can hold all my tools in here. I've got a small pocket for whatever bolts I might need, and this is also strapped on over the belt, over your safety belt, your work belt, and now I can work up on top of the tower with my hands free, safely, and all of my tools are right where I need them. A lot of wind generators have some sort of a crank mechanism on it, and I can uncrank the tail, and if we look at what's going on up on top of the tower, you'll notice that as I uncrank the tail folds or furls, and it's going to force the blades out of the wind. And once they've stopped spinning, we can climb the tower and go up and do our maintenance work on it. That's a very good safety feature, because the last thing that you want to do at any point is work up on top of a tower with spinning blades. You could get very, very hurt, if not very, very dead, by doing something like that. Quite dusty up there on the wind. The blades are still spinning a little bit, but they've slowed down sufficiently that it would now be safe to climb the tower and to get up around the wind generator and do any maintenance that you needed to do, or do any checks that you might want to on fasteners, bolts, nuts, to make sure nothing is chafed or loosened up. What goes on with lightning is we've got a fluid passing over the surface of the earth, and it's not unlike you walking across carpet with your bare socks in the wintertime and developing static charge on yourself, and you walk up to your favorite cat and zap it on the nose and you don't see it for 2 weeks again. What you did was you sort of developed a static charge based on you scruffing your socks on the carpet. Well, the same thing happens with when the air passes over the surface of the earth. When the air passes over the surface of the earth, it develops a static charge on various different objects that are sticking out of the earth, trees, towers, buildings, and what we want to do is we want to dissipate that static charge, because lightning is attracted to that static charge. So we want to dissipate that somehow. The way we do that is by taking a ground rod like this one. It's an 8-foot copper-clad steel rod, and we drive it into the ground. We beat it down into the ground with a sledgehammer. And then once it's sticking out of the ground about 3 or 4 inches, we take a strap, a copper strap, and attach it to the tower legs. You do this on all 3 legs. You can see the copper strap is attached to near the corner of the tower leg here. There's a wire connected to this, and this wire would go down and connect to this ground clamp. This clamp connects this strap and wire to the ground rod, and that helps dissipate the static charge that develops on the tower. And in case of a direct lightning strike, what would happen would be this lightning arrestor would take the lightning that came in on the wires, for example, and it would ground it out right down in through my ground rod, and we'd hopefully dissipate that lightning strike that way. The wind generator that's on the tower out there is feeding through a system of electronics directly into the grid. So what we're using for storage in this case is not a battery bank, but instead the utility itself, the grid network itself. The way it works is the wind generator power comes into a series of synchronous inverters which convert the DC power that the wind generator's producing directly into 60-cycle AC current, and it puts it back onto the grid. It matches it perfectly for frequency and voltage, and what varies then is is the current going into the system. We can take a look at the wind generator voltage and current based on what the wind speed is. There's a couple of meters here. This meter is for another wind generator, but this meter here is monitoring the amount of electricity that the Jacobs itself is producing. The only thing on this meter is the Jacobs wind system. And what we can do now is we can go take a look at the house kilowatt hour meter and see what we're using, what the house is using and the shop is using, and how much we're selling back to the utility. Okay, let's see what's going on with the kilowatt hour meter. If we take a look at it, as the wind speed increases, meter's running backwards in this direction, which is telling us that the wind generator is producing more power than we're consuming. But as various different people do different jobs in the shop, it may actually slow down, stop, and there you see it going forward. So depending upon how much wind it is and what the loads are, the wind generator will cause it to run backwards, which backfeeds excess power right into the grid.